Okay, so our next speaker is from the University of Arkansas, and he'll be speaking about, Z Jiang, and he'll be speaking about barium zirconium titanate and lead magnesium niobate relaxer ferroelectrics, the electrochoric effects from atomistic simulations.
Good afternoon, everybody. My name is Z Jiang from Xi'an Jiaotong University. Today, my title is about electrocaloric effect in barium, zirconium, titanate, and PMN relaxer ferroelectrics from atomistic simulation. First, I will introduce my co-authors. Dr. Lenhans Prokohorenko, Dr. Prosandi, Dr. Wang, Dr. Hogi, Dr. Edifi, and Professor Bleich. The second is I will thank the support of the DERPA, NSCF, China Scholarship Council, and AHPCC. My talk my outline is about first is introducing, second is methods, three is results, the last one is conclusion. First, I will introduce the caloric in application. The first paragraph is the electrocaloric material change in phase change when we apply electric field, induce phase change. Second is the thermal change when apply a magnetic field to get the thermal change. The third is the experimental measures the infrared imaging to get the caloric effect. This circle is about the diagram of the caloric refrigeration cycle. The field we can apply the electric field, magnetic field, or another string, or so on. Next is what practical application can caloric effect be used in? Last talk about Professors Rapi and Dr. Hill also say it's about the solid color system which used in solid material and can reduce the impact. Can reduce the impact of the environmental. Can be reduced the green's impact. The second is about the electrocaloric effect. Last two talks also induced more about this electrocaloric effect. So I just briefly say this electrocaloric effect is the change in temperature when induced by change of electric field. This picture is the same as Dr. Steckhill just talk about the dipole from when there is no electric field, the dipole is disordered. When apply electric field, the dipole from disorder to orders induce the entropy decrease, then the temperature increase. So I don't say more about this one because Dr. Steckhill is also say more about this one. The second is the potential designs of the dual electrocaloric refrigerators and schematic of the components. This is the potential they use to design the electrocaloric refrigerators. Some more data, please see the reference. In order to understand the EC effect in relaxers, we have need to solve a lot of questions. The first one is can direct and indirect measures provide different results below a specific temperature? The second is how does EC coefficient behave with the DC electric field for different temperature range? The third is can EC coefficient exhibit maximum for some intermediate field and different temperature range? The last one is how to understand the EC effect from its microscopy. So we choose two relaxers. The first one is BZT, second one is the prototypical PMN relaxer ferroelectrics. First, I will introduce our method. Our method is based on effective Hamiltonians. This is our total energy. The first one is mu I is represent local mode and each site. The second is inhomogeneous string. The third is homogeneous string. This is a solid solution configurations. So we introduce the first method is indirect method. This indirect method is based on the Monte Carlo simulations. Also, it's based on the Maxwell thermodynamics relations. From this one, we can get the delta T change and the alpha. The alpha represent the electrocaloric coefficient. Here, we call this method is MC1. The second method is also the MC simulation. We call it based on the cumulant method. More detail, please see the reference. So the indirect method have two. The first is MC1. The second is MC2. MC1, MC2, both based on the Maxwell thermodynamics relationship. The second is the molecular dynamics simulations direct method. Here, we first choose the initial temperature, then rampings increase the electric field to epsilon to EF. Then we can get the delta T change. Then we can calculate the alpha. The alpha is the EC coefficient, can be obtained by taking the derivative of the delta T with respect to the different value of EF. So this method we call MD. This is a direct method. Our Hamiltonian in BZT predict series specific temperature. The first one is Tm is about 130 Kelvin. The second is the critical temperature. T star is about 240 Kelvin. The third one is T Bourne's temperature is about 450 Kelvin. This temperature is a good agreement with the experiment. So we use the MC1 method, the indirect method, to calculate the polarization and the function of the temperature. Then we can, according to the delta T formula, we can get the delta T as a function of delta E. The important thing is we got the EC coefficient as a function of electric field for different temperature. Here we choose four different temperature. One is 100, 200, 300, and 500. Why we choose the four different temperature? Because 100 Kelvin is below Tm, and 200 is between Tm and T star. The 300 Kelvin is between T star and T Bourne's. 500 is above Bourne's temperature. So, from the picture, we can see that above the Tm, the three methods can get nearly identical results. But below Tm, the indirect and direct method can't get the same results. Because below Tm, the system is non-ergodic. We can't use the normal Maxwell thermodynamic method to calculate the real EC effect. So we don't, here we don't trust the indirect method, we just trust the direct method. Though, to understand the EC response and the function of electric field, we, based on the Landau mode and derivative, the alpha is proportional to the derivative p squared with respect to the electric field. In other words, the alpha is proportional to this formula. To verify this model, we calculate the polarization, square of the polarization as a function of electric field, then take the derivative. We can find that the trend is the same as what we found before, just like this one. This is the EC coefficient as a function of the electric field. We use the lambda-based models also can copy this trend. So next step, we also calculate the microscopic insight. This is the percentage of dipole lying along 1-1-1 direction, but we choose have positive Z component. So there should be have 4 direction. Here, sorry, I forget to remember this. For BZT, our applied electric field is along 0,001 direction. So there is 4 direction. From the picture, we can see that the ratio of the percentage of dipoles as a function of electric field have a peak around 1.2 by 10.8. This electric field is the peak is associated with the EC coefficient as a function of electric field. In other words, we calculate the percentage of dipole lying along different directions, can understand the microscopic insights, just the rearrangement of the dipole to understand the EC response. The next is EC effect in PMN, in prototypical PMN relaxer. Here, we apply electric field is along 1-1-1 direction. Why we choose along 1-1-1 direction? Because experiment already is predict the when you apply 1-1-1 direction along in PMN, there will occur first order transition. This is our simultaneous predict the polarization as a function of electric field. We found that below a specific temperature, there should occur the first order transition, and 320 Kelvin and 350 Kelvin is first order transition, but equal or above the 360 Kelvin, it from first order transition become to second order transition. So this temperature should be the critical point in PMN. Next, we plot the phase diagram for different temperature. Here is the first order transition lines. We also plot the percolating lines, rhythm line, and alpha max line. I will see later. Then we calculate the calculate the electrocaloric effect coefficient for different temperature. Why we choose the 2 temperature? Because this temperature is near the critical point. We also show that the critical point is about 360 Kelvin. So we choose this temperature is near the critical point. This temperature is far away from the critical point. From the picture, we can see that we find a giant EC response at intermediate electric field. This magnitude electric coefficient is agree with the experiment. In other words, we also find a giant electrocaloric response or near the critical point, just near the first order transition. But at higher temperature, we also find this value is also bigger. In other words, in PMN, near the critical point, we'll find a giant electric response, but higher temperature is also have a bigger electrocaloric response. This picture, we just use the MC simulation based on the cumulative method. Why we just use this one? Because in PMN, about the ergodic, we just can use the indirect method. But below the below the critical point, we can't use this formula because this is can't use to calculate the electrocaloric effect. Then we also use the lambda-based model to fitting our EC coefficient and function as a function of electric field. We can see that this model can get very good fitting to our data. Next is we calculate the alpha max as a function of temperature. We find near the critical point, we find giant electrocaloric coefficient. This is agreed well with the experiment found. Next is percolating in PM. I first introduce the two parameters. The first is the strength of the percolating cluster. The second is average cluster. The N infinite is represent the numbers of the lead sites belong to the percolating cluster. This is the lead site in all the supercell. The second is about the N. The N represents the number of the cluster size belong to the polar region. So use this two parameter, we calculate the percolating in PMN. We found, and we also choose the two temperature because before we can calculate the EC response for the two. Found that, and this electric field change, the system begin to percolating. This field range is associated with the alpha max. Is associated with the alpha max we found. But at 500, because the cluster size is smaller than 308 Kelvin, so we need more bigger electric field to percolating this system. This is the 3D snapshot of the dipole configuration at 300 Kelvin. And when there is no electric field, we can see I need to introduce is the green line is along 111 direction because our electric field is along 111 direction. When there is no field, we can see the system is no percolating. But when we choose the percolating electric field, we found the percolating through all the supercell. Next is about the local feature in PMN. We also calculate the percentage of dipoles lying near the 3 rhombohedral direction. Why we choose the 3 direction? In BDT, we choose 4 because in BDT, we apply the electric field is along 001 direction. So BDT is 4 direction. But here, we apply electric field is along 111 direction. So here we just have 3 directions. We find this percentage of dipoles have a peak and intermittent electric field. This field range is associated with before EC response. We also check at more bigger temperature. You can see this is the EC coefficient and function of the electric field. We find peak around 1,000 kV per cm. We also found this peak is associated with the local features, just about the percentage of dipole. The last is the conclusions. EC effect in BDT and PMN. First, we get for any temperature, alpha exhibit no monokinetic behaviors with DC electric field. The second is the maximum alpha for given temperature is related to some specific local feature. The local feature is we choose dipoles along different rhombohedral direction. The third is we use a simple lambda-like model to reproduce the EC response. The fourth is a giant EC response occur near the critical point in PMN. This is also agree with experiment results. The last is giant response induced by field-induced percolating of polar region. Thank you for your attention.
Okay, thank you. So are there any quick questions in the audience? Yeah, if not, our next speaker could come up. Does anyone have any questions? Yeah, please.
I'm a little bit confused by your second case. Why you apply electric field along 111 direction, right? But
Yeah.
you also calculate the percentage, right?
Yeah.
But why it's peak at an intermediate electric field?
What?
Why the peak is at the intermediate electric field?
Because from the lambda-based models, it should have no monotonic as a function of the electric field.
I'm just saying you apply electric field along 111, isn't higher electric field just going to align more dipoles along that particular direction, and therefore you have a higher percentage of dipoles along that particular direction?
Yeah, but you mean this one?
The next one, right here.
This one?
Yeah.
Yeah.
No, the figure on the left. The R is the percentage of dipoles lying along the 111 direction, right?
No, just the percentage of the line there. This is not 111 direction. We just accept the 111 direction. Just choose 3, 1, negative 1, 1, 1, negative 1, and negative 1, 1.
Yeah, why the curve doesn't keep going up? Yeah.
Because initially the dipole is disordered when we not along 111 direction. When we apply the electric field along 111 direction, maybe some dipole want to must change his direction to 111 direction. So we just calculate the how many dipole along different 111 direction want to change.
Okay, so basically you're calculating the percentage of dipole that are not aligned with electric field. Is that okay?
Yeah.
Okay.
This is not along the electric field. Electric field is along 111 direction.
Okay, I think with that and in the interest of time, let's thank our speaker once again.